Welcome back from break. Now we are going to continue talking about the topics of chapter 6. We are going to move on now to talk about electronegativity and bond polarity. So now that we know how, if we have certain atoms in a covalent compound, how they come together to make those covalent compounds in which we find bonds that are going to share electrons, now we are going to learn how those electrons are going to have effects on which atoms are going to be able to attract more electrons or less to themselves. And that is the concept of electronegativity. As you can see, in terms of the bullet points that we have on the left side of the slide, electronegativity indicates the attraction of an atom for the shared electrons in a bond. There is a trend in electronegativity. That being said, when it comes to electronegativity, you can see that in the reference list for exams, I already given you guys a periodic table that has the values for electronegativity. So when we look at electronegativity, understand that the most electronegative atom is fluorine. If we pay attention to the numbers as we move from left to right in the periodic table, we see that the values in electronegativity are going to increase. So the trend in electronegativity when we move from left to right in the periodic table is that we see an increase in electronegativity. Now, if we look at atoms in groups, okay? So if we are moving down, up in the periodic table, we can see that also there's an increase in the values for electronegativity. So understand that those are the two trends. Electronegativity increases as we move from left to right in a period, or if we're in a group, if we're moving from the bottom part to the top part, we see an increase in electronegativity. Understand that for electronegativity, you do not need to memorize these numbers, okay? I don't even have them memorized. I think I know maybe like 5 atoms. Like I know fluorine for sure is 4.0. I know that hydrogen is 2.1, you know, carbon 2.5, and maybe oxygen, you know, 3.5. But I don't memorize this. But you guys need to know how to utilize this table with these values for the concepts that we're now going to discuss. So understand that this table, it is something that you need for exam 2. As you can see in the other bullet points, and you can see it based on the trends and the numbers that we see here. Electronegativity is high for non-metals, okay? And it's low for metals. And again, those are the trends. This is based on the Pauling scale. This is Linus Pauling who created these values for the elements in the periodic table, okay? Now, how are we going to utilize this concept of electronegativity when we're dealing specifically with bonds? So we have seen so far that there are different types of bonds depending on the molecule. We have covalent bonds and we have ionic bonds, and those are going to be the general families. Now, out of those two families, the covalent bond actually are going to divide further because we can have nonpolar covalent bonds and we can have polar covalent bonds. Ionic bonds do not divide further, okay? So how are we going to utilize the concept of electronegativity to actually determine the polarity of a bond in the following manner? So here we have three different molecules. The first one is Cl2. The second one is HF. And the last one is NaCl. Okay? So Cl2, if I look at its Lewis dot structure, it looks the following way. Now, if I'm trying to define what type of bond is this, then what I need to do is look at the electronegativity values of the two atoms that are connected by that bond. In this case, I'm comparing chlorine to chlorine. Chlorine has an electronegativity value of 3.0. So when I subtract it to itself, it gives me an electronegativity value of 0. And as you can see here, if you have electronegativity values in between 0 and 0.4, that means that that is a nonpolar covalent bond. So again, the values for nonpolar covalent means that the values are going to be from 0 to 0.4. Okay, let's now look at HF. Okay, so in the molecule of HF, I'm just going to draw the Lewis structure for hydrogen monofluoride in the corner. It looks in the following manner. So if I'm trying to define what type of bond is this, I'm going to do the same exercise. I'm going to look at the difference between the two atoms that connect that bond, okay? So understand that when it comes to this subtraction, you're always going to get a positive number. You're always going to do larger electronegativity value minus smallest electronegativity value. So as you can see here, for HF, in order to define that type of bond, I'm going to do 4.0, which is the electronegativity value for fluorine, minus 2.1, which is the electronegativity value for hydrogen. So that gives me a difference of 1.9. As you can see here, because my value is higher than 0.4 and less than 2.0, then that's why this bond is a polar covalent bond. Again, polar covalent, it has to be larger than 0.4 all the way to 2.0. Let's lastly look at NaCl. The Lewis structure of NaCl represents that sodium lost its valence electron, and now the chloride ion has 8 valence electrons. That is the Lewis dot. Now, ionic bonds are not represented by a line. As we learned earlier this week, in an ionic bond, we have an electrostatic interaction. So it's that interaction between that positive charge in the cation and the negative charge in the anion. Okay, so we're not going to draw a line for ionic bonds. But in order to identify that electrostatic interaction, again, we can utilize electronegativity values to do so. So when we look at this, we can see that If we compare chlorine, which has an electronegativity value of 3.0, to the electronegativity of sodium, which is 0.9, the difference is 2.1. And because my value, again, is larger than 2.0 up to 4.0, that shows that the bond between NaCl is going to be an ionic bond, okay? Any questions on trying to determine if you're given a molecule or a pair of atoms, what is going to be the type of bond that is found between them? Put a 1 in the chat if you understand this concept.
Professor, I have a question.
Yeah, go ahead, Thea.
So where did you get the number like 4.0, 2.1, 3.3, 3.0? Like where can I locate that in the periodic table?
Right there.
Gotcha, I just missed those numbers. Thank you.
So this table specifically, it is found on the reference list for exams. So that's why I say you need for exam 2. It's already pasted there in the reference list for exams. Also this, the one that you see below the different atoms here, because these are just histograms. This is just molecules that are generated. Also that range between 0 to 0.4, higher than 0.4 to 2.0, higher than 2.04. So that is also in the reference list for exam.
Okay, thank you.
No problem.
So the basis of finding if something is nonpolar or a polar, covalent, or ionic is based on the electronegativity numbers that are given on the table. So like you said, sodium and chloride, if sodium has 0.9 and chloride is, I just saw it, whatever chloride is, you would take those two numbers, subtract them, and then that would tell you if it's an ionic, covalent, nonpolar, or polar bond.
Yes, this is one of the indications for polarity of a bond, because this is going to be separate from polarity of the molecule. So now I'm introducing of, like, you guys know how to draw the molecules. Now let's define the bonds that we find in molecules. So this is the first step into understanding polarity overall, because this is a subject that is a little bit more broad. So there's a question in the chat about ionic bonds. So what is holding ionic bonds together? Think about it in terms of analogies, like a magnet. That positive and that negative side of a magnet is what attracts magnets together. Similarly, in ionic bonds, having that cation and that anion that are opposite in charges is what's keeping those two atoms together. That's why this is called an electrostatic interaction, plus minus. And then these are very strong, because if you think about it, ionic compounds make solids. Solids have strong interactions. Now, these interactions can go away as long as, we're going to see that later, depending on the molecule that they're interacting with. But what is keeping an ionic bond together is that cation being paired with an anion, that electrostatic interaction, similar to magnets, plus minus, is what's creating that ionic bond. So you do not write a line. It is incorrect to write a line in between the cation and the anion in ionic compounds. Yes, it is called an electrostatic interaction. Now, when it comes to polar covalent bonds, okay?
Professor, I have a quick question.
Yeah, go ahead, Alexa.
Yeah, okay, so is this, is that because it's the positive charge and the negative charge are attracted to each other? So if it were a positive and a positive and they repel each other, what would happen in that case?
That is a great question. So that is why throughout all the discussions that we have had in chapter 6, we have never seen compounds that have the same charge that are attracted to one another, right? I never told you what is the compound that can be made when magnesium interacts with calcium. They are both going to make cations. They cannot be next to one another because they have like charges. Those compounds can never be seen. Furthermore, earlier we learned in chapter 3 about the different type of substances. Think about it. Alloys are going to be metals that are physically mixed, but they're not chemically combined. So for example, steel, which is made out of iron and carbon. Those two metal, well, carbon is a non-metal. Let me just backtrack on that one. But bronze, for example, that would be a better example. When we have copper and zinc, those are two metals. So they are not going to be specifically, chemically combined with one another. They're just sitting next to one another in order to make that alloy. So to date in chemistry, there are no examples that have been documented in which you have two metals that are chemically combined to one another. Again, I don't know what's going to be the state of chemistry from here to 10 years or 20 years, but to date, for ionic compound, what we have always observed is positive with negative, never positive with positive or negative with negative, because like you just said, those like charges will repel each other.
Thank you.
No problem. But going back to the concept of steel, steel is just a product of just taking carbon in ground state and iron in ground state and mixing them together to make that alloy, even though that is a metal and a non-metal. But for that material, it was possible for them to, at ground state, mix with each other and not make a chemical bond between that metal and non-metal, in the case of steel. So, one more thing about the types of bonds. We have to establish that polar covalent bonds are going to have different markings compared to nonpolar and ionic, okay? So as you can see, when I did my Lewis structure for sodium chloride, when it comes to ionic, we need to represent what is the cation, and you can see that I wrote in a solid positive sign on top of sodium, and we have to establish what is the negative, the anion, and that's going to be chloride in this case. Now, polar covalent bonds, because there is a separation of charges, those polar bonds are said to have a dipole. And dipole, just like the name implies, di, two poles, that's the two ends. In a polar covalent bond, we're going to have two ends, one that has a higher electronegativity value versus the other one, okay? Now, in polar covalent bonds, we can actually use symbols to illustrate that difference in electronegativity between the two atoms, okay? So we can see here some examples of polar covalent bonds and the different notations that we can use to symbolize the dipoles that they have. So when we compare carbon to oxygen, and again, I have not have these memorized. So we have carbon and oxygen 2.5 and 3.5. So oxygen is 3.5, carbon is 2.5. So as you can see, the difference between them is 1.0. So it makes sense. It's a polar covalent bond. Now, we can show the dipole in this polar covalent bond by using the Greek symbol delta and then a little sign showing that, hey, in a carbon-oxygen bond, there is a dipole because this is a polar covalent bond, and that delta sign shows that when we have polarity here, carbon is more electropositive compared to oxygen. The reason why we use the delta symbol is because the delta symbol is representing a partial charge. So you may ask yourself, okay, Dr. Luz, so how different is this from a cation? Very different, you guys. Because remember that what is unifying carbon and oxygen in this case is sharing electrons. What this delta represent is that if we're in a tug of war between carbon and oxygen, because oxygen is more electronegative, the electron density can be pulled towards oxygen a little bit better than carbon. And that's why there is that polarity. There's that dipole existing between carbon and oxygen. So if we compared nitrogen and oxygen, similarly, oxygen is more electronegative than nitrogen, okay? So that's why you have delta plus, delta minus. Understand that this designation is only for polar covalent bonds. The other way that we can illustrate that dipole in a polar covalent bond is by the use of drawing a vector, which you can see that is that arrow in the bottom. In terms of utilizing a vector in order to indicate the dipole in a polar covalent bond, the tip of the arrow is going to be pointing towards the most electronegative atom. Any questions when it comes to determining the polarity of a bond? Then let's do an application. So these are the Lewis structures that we generated a few moments ago. So now let's take a few moments and determine what are the different bonds that these molecules have, okay? So utilizing the table that we had, we are going to determine the types of bonds that are here in each of these molecules. In the case of H2S, we're comparing hydrogen to sulfur because that's the only type of bond that we have there. In the case of beryllium bromide, we're comparing beryllium to bromine. In the case of sulfur trioxide, we're doing sulfur to oxygen. In the case of HCN, we're going to do hydrogen to carbon, but also carbon to nitrogen. And again, I don't need to include the triple bond because I'm just looking at the bond as a unit. So we're trying to define what type of bond is that triple bond. When it comes to carbonate, is just carbon oxygen, which we just know that that's a polar bond because that's the example that we just did. And lastly, when it comes to chloride, we're comparing chlorine to oxygen. Remember how we're going to get these numbers from the table that I gave to you guys, or I illustrated a few moments ago. So let me just fill in the values that I know from top of my head. This is 2.1. This is 2.1. Oxygen is 3.5. 3.5. 3.5. Let me go back. Sulfur is 2.5. Bromine and beryllium. Bromine is 2.8. Beryllium is 1.5. Bromine 2.8 and 1.5. Great. 2.8. Sulfur is 2.5. carbon is 2.0. Oh no, this is 2.5, not 2.0. 2.5, 2.5. Nitrogen and chlorine are the only things missing. 3.0 and 3.0. So I'm going to give you guys 2 minutes to determine the type of bonds that we have in each of our molecules. I already provided to you the values for electronegativity. Understand that in an exam, when I'm asking the type of bonds, this is how you perform it. I'm not going to give you the values of the electronegativity for every atom because I already illustrated to you guys how to obtain them. So you guys have 2 minutes to determine the type of bonds in these molecules. Okay, let's get started. So the difference between hydrogen and sulfur is 0.4. So that means that hydrogen and sulfur, this is a nonpolar covalent bond. Okay, so if you land at 0.4, you're still nonpolar covalent. If you land at 2.0, you're a polar covalent bond, not ionic. Next one, the difference between beryllium and bromine in terms of electronegativity. This is 1.3. So this is a polar covalent bond. For sulfur and oxygen, this is a difference of 1.0. So what kind of bond is it? Excellent, polar covalent. Now, when it comes to HCN, what kind of bond is a hydrogen-carbon bond? Great. This is non-polar covalent bond. What about carbon and nitrogen? Excellent. This is polar covalent bond. Great job on the chat. So let's just finish these guys. We already learned that carbon oxygen is going to be a polar covalent bond. And lastly, chlorine oxygen. This is a polar covalent bond. Any questions determining the types of bonds in a molecule?
When we're, Professor, if we're given, so like for D, if we're given 3 different elements, when we give an answer, we have to separate the elements, and that would be our answer would technically be 2 answers rather than just 1, correct?
Yeah, like in the example of HCN, like you said, because there are 2 types of bond. You know, there's the carbon hydrogen and then the carbon nitrogen. So that's why we needed to take them separate. So as long as you have atoms that are different, you need to specify in the context of this molecule, by definition, what type of bond is this pair versus the other pair.
Thank you.
No problem. Go ahead, Victoria.
So there is no bond between hydrogen and nitrogen in example D? If I'm looking at example D, there is in fact no bond between hydrogen and nitrogen, is that correct?
Exactly.
Thank you.
No problem. Remember, what we're trying to define here is if we have elements that are with each other in a molecule, what type of bonds do they have? Okay, because remember that in essence, these atoms are going to be interacting to one another via the central atom, right? So just because you are part of a molecule, that doesn't mean that they are all connected, as you guys can see illustrated in example D. Even though in a molecule we have hydrogen, carbon, and nitrogen, everybody is attached to carbon. So the only bonds that we actually see are hydrogen and carbon and nitrogen. You cannot be doing a calculation for hydrogen and nitrogen because when you look at the molecule, they're not bonded to one another. Excellent. So put a 1 in the chat if I give you a molecule or I give you a pair of atoms, you can tell me what type of bond is connecting them. Excellent. I love to see those ones. Now, why do we need to learn about bonds and polarity and all this good stuff? Because it is important to note that when we have molecules, these molecules, each atom is going to have electrons. And sometimes these electrons are going to be shared. But as we discussed a few moments ago, these electrons, because they have like charges, meaning that they're negative, that is going to actually make molecules adopt 3-dimensional structures, okay? So for example, here we have the molecule CH4, okay? So this is called methane. So CH4, because of what we have discussed so far, has the electron dot formula that is given by the molecule all the way to the left, this one. Now, because when we look at the molecule overall, these atoms are going to be sharing electrons. Those electrons are going to be like, I need my space. Please don't touch me. I'm just going to make the central atom adopt a three-dimensional structure. So I see you, I feel you, but I'm going to be far away from you. So the hydrogen atoms around that central atom adopt what is called a tetrahedral electron group geometry. There is an angle that is defined of how separated are these bonds to one another. In a tetrahedral molecule, you see that they're separated by an angle that is 109. Furthermore, if you have a molecule that is tetrahedral, we can draw it in a three-dimensional structure in which you can see that this bond, I'm going to use my highlighter tool that I'm highlighting in yellow, which is going behind the plane. We are illustrating it with a dash. This bond, which is facing towards us, okay, is going to be illustrated with a wedge. Now, if we think about the system, these two atoms right here, the ones that I'm highlighting in green, are in the same plane. So that's why when we draw it, we draw them in the same plane. And again, this is how we draw in a three-dimensional way, okay, a tetrahedral molecule. Now, all of these concepts are actually derived by what we called in chemistry the valence shell electron pair repulsion theory. So this has a base, meaning this has some important basis of why is it that this happens. And instead of saying all of those words, valence shell electron pair repulsion theory, we just summarize it as Vesper rules, okay? And you can see that this theory is what describes the orientation of electron groups around a central atom, okay? It tells you how these electron groups are arranged as far apart as possible. And remember, that comes from the idea of the electrons, since they have like charges, they repel each other, and that's why this happens. And it tells you what is the specific shape of a molecule. Again, this is all according to what is this happening in comparison to, or around, I should say, around the central atom, okay? So as you can see, the first thing that we need to learn here is this concept of what is an electron group? So if I'm given a molecule, how do I know how many electron groups are out there? Well, electron groups, remember that they are going to be specifically groups of electrons. So electron groups come in 4 flavors, and they each represent 1 electron group, okay? So let me just write those in words so you guys have it in your notes. Each represent 1 electron group. And the 4 flavors of electron groups are the following. A lone pair of electrons is 1 electron group. A single bond is 1 electron group. A double bond is 1 electron group. Even a triple bond is 1 electron group. So for example, here we have the molecule, okay, NO2. So this is NO2. -1. So this is nitrite. Let me see if that makes sense. Yes, so this is nitrite. So when we look at nitrite, we're going to see our central atom, okay? Our central atom is that nitrogen. Okay, now we look at our central atom and we say, okay, how many electron groups are around nitrogen? And you can say, oh, there's one lone pair. There's one single bond. There's one double bond. So there are 1, 2, 3 electron groups around nitrogen. Okay, so taking that into consideration, I'm going to give you guys, I'm going to do the first one, but I want you guys to determine, looking at the structure, how many electron groups are in each of these atoms. I'm going to start with H2S. There are 4 electron groups around the sulfur in H2S. What are the 4 electron groups? A lone pair, a single bond, and a single bond. Letter B, around beryllium, there's 2 electron groups. A single bond and a single bond. Let's use the chat, and I just want numbers. For sulfur trioxide, how many electron groups? Excellent. I want people to join. Exactly. Great. Let me see that people get it. I love to see those 3s. Excellent. So this has 3 electron groups. Letter D. How many electron groups around carbon? There are 2 electron groups. For those students that are like, wait, what? Yes, there's 2, a single bond and a triple bond. How many electron groups around carbon in carbonate? There are 3 electron groups. A double bond, a single bond, and a single bond. How many electron groups around chlorine in chlorite? Great. There are 4 electron groups around chlorine in chlorite. Questions on how to determine the number of electron groups.
Professor,
Yes, go ahead, Elle.
in the worksheet, for example, would the would 4 electron groups go in the section for electron group geometry in the worksheet?
That's what we're going to do next. Of how to
okay.
define, if we know the electron groups, how we're going to use the table to determine electron group geometry, shape, angle.
Okay, all right, thank you.
There's a question in the chat about the whole idea of a triple bond. Remember, when it comes to electron groups, A lone pair is one electron group. A single bond is one electron group. A double bond is one electron group. A triple bond is one electron group. So it counts as one. So any of those flavors, lone pair, single bond, double bond, triple bond, is one electron group. So put a 1 in the chat if you understand how to define what are the electron groups in a molecule. Again, remember that all of this, we are just building knowledge. We go from knowing elements to drawing molecules to understanding the bonds that are in there to defining electron groups. And now we're going to say, how do I find for my molecule, what is the electron group of it? What is the molecular shape? And what is the bond angle? So this table, you guys, which is also in the reference list for exam, you need to know how to use for completing your homework, okay? So you need this for exam 2. I'm going to teach you how to utilize this table, okay? So you can see this table is defined by the different rows, okay? So if we look at electron group 2, so I'm just going to zoom in so we follow. If something has an electron group of 2, and I ask you, what is the electron group geometry for that molecule? Your answer will be linear. In many examples, you will see that in linear molecules, you have only 2 bonded atoms. The bond angle for something that is linear is going to be 180 degrees. Then you will see that, oh, the molecular shape is also linear. What is the difference between electron group geometry and molecular shape? Electron group geometry just tells you in general how many electron groups are around the central atom. The molecular shape takes into account if you have bonded atom versus lone pairs at the level of the central atom. That's the difference, okay? So they're related to one another, but the molecular shape may be different depending if you have lone pairs or not. Let's move on to when you have 3 electron groups. At the level of 3 electron groups, okay? If you have 3 electron groups, your electron group geometry is always going to be trigonal planar. Always, always, always. Now, also the angle will be 120. That angle of 120 means what? That's the separation, the angle that exists between the bonds. Now you can see that the molecular shape is affected by the lone pairs. Because if you have 3 bonded atoms around the central atom, but no lone pairs, then you're trigonal planar. If the central atom has 2 bonded atoms and 1 set of lone pairs, then that means that the molecular shape is called bent. Put a 2 in the chat if so far reading this table makes sense. Excellent. Let's move on to the last part. Let me see if I can put them here together. And that is if we have 4 electron groups around the central atom. The electron group geometry for any central atom that has 4 electron groups is going to be tetrahedral. Okay, the electron group geometry for anything that has 4 electron groups is called tetrahedral. The angle is 109 degrees. Now I want to specify this for students that have taken chemistry 100, or if you have taken high school chemistry and all that kind of stuff. In this course, I simplified this concept by saying if something is tetrahedral, it's 109. For the students that have taken other chemistry courses and maybe taking other courses, understand that it is true. If your central atom has 1 or more lone pairs, that actually changes the angle. But in this class, I'm just going to simplify the concept and say, you know what, you guys, anything that is tetrahedral, my angle is going to be 109. Maybe you have heard that this angle is 109.5. That is okay. All of that information is correct. I'm just trying to simplify the concept here. And when I test you, is based on that concept that I'm teaching you here. So understand that for the purposes of this class, something that is tetrahedral is 109, regardless if there's lone pairs or whatnot on the central atom. 4 electron groups is a 109 bond angle. Now, as you can see here, if my central atom has only 4 things bonded to it, then my molecular shape is also called tetrahedral. If my central atom has 3 bonded atoms and 1 lone pair, then that molecular shape is called trigonal pyramidal. If my central atom has 2 bonded atoms and 2 lone pairs, then that molecular shape is considered bent. And that's how you utilize this table to understand what is bond angle, what is electron group geometry, and what is molecular shape. So taking that into consideration, we already built, okay, the Lewis structures for these molecules. And in a table like this is what you guys are going to see for the practice problems that are coming in the next lab, okay? So in lab 5, you guys will be practicing Lewis structures and all this kind of stuff. So I just wanted to introduce this in the table that you will be encountering in the lab next week, okay? So we also determined already the electron groups for the following molecules, right? Let me just fill that in. In terms of electron groups, this has 4 electron groups. This has 2 electron groups. This has 3 electron groups. This has 2 electron groups. Okay. I'm not going to fill in the information for the valence electrons, but understand that that is going to be necessary for the lab. So let me just at least erase this information because we already done that. I'm going to focus on what we have here. Again, utilizing this table. So if I ask you guys for H2S, okay, what is going to be the electron group geometry? Let's put it in the chat. Electron group geometry. It's not linear. There's nothing linear on 4 electron groups. Exactly, tetrahedral. Look, this is all I'm doing, you guys. I'm saying this has 4 electron groups. Oh, 4 electron groups means tetrahedral. Let's look at the next one. 2 electron groups. What is the electron group geometry for Beryllium bromide. Excellent job. Linear. Okay. Let me go back to the first one, H2S. H2S has 2 bonds and 2 lone pairs. So what is its molecular shape? So H2S, what is its molecular shape? Great job. This is bent. What about for beryllium bromide? What is its molecular shape? Molecular shape for it. Excellent. Thank you. Also linear. Because we can see here how if you have 2 electron groups, your electron group geometry is linear. Okay. So sulfur trioxide, what is its electron group geometry? Great job. Trigonal planar. Okay. Where did we got that trigonal planar from? 3 electron groups. 3 electron groups is trigonal planar. Now, if I look at sulfur trioxide, what's going to be its molecular shape? Great, also trigonal planar. And lastly, for HCN, we have a linear and linear answer. So the electron group geometry is linear, molecular shape is also linear. For those students that are like, wait, I don't get it. 2 electron groups. And as you can see, 2 electron group means group electron group geometry that is linear. Okay. So put a 1 in the chat if you know, at least if you have a Lewis dot that you built, you know how to identify the electron groups, determine electron group geometry and molecular shape. And you guys, whenever you're doing these problems in the assignments, in the extra credit and the exam, is always the same process. Build the correct Lewis structure, determine the electron groups, then utilizing this table, determine the electron group geometry and the shape. And remember that the shape is going to depend on bonded atoms versus lone pairs. So I'm going to fill in the angles. So for 4 electron group is 109 degrees. For 2 electron groups is 180. And for 3 electron groups is 120. Okay. So I just wanted to include the bond angle. Any questions before we move on to the next concept? Excellent. So now that we know how to build the molecule, determine the electron groups, find the electron group geometry, now we need and find the type of bonds that are in there. Now we are going to focus on molecular polarity. What is molecular polarity? Molecular polarity is going to be based on the overall picture of the molecule. And what this determines is if I'm dealing with a polar molecule or a non-polar molecule. You may be asking like, oh my God, all of this process to understand what? Well, one of the things that all of these concepts tie together is when we have a particular substance, their behavior is based on all of the concepts that we have discussed so far. the type of bond that it has, the type of structure that it has, the type of electron group geometry, shape. Because remember that when these molecules are interacting with each other, they're going to do it in terms of their 3D structure, because that's how they exist. Molecules are not going to exist flat as Lewis structures. That was just the first part of it. In understanding the polarity of a molecule further, it actually tells you how these molecules are going to have attractive forces that are going to explain their behaviors, or even if you put them next to each other, why is it that they repel each other, right? For example, the majority of you, I hope, know that oil and water don't mix, right? Put a 2 in the chat if you know that oil and water don't mix, right? That is something that is in common knowledge. And you grew up knowing this, and you're like, oh yeah, oil and water don't mix, you know? And then you will be like, but wait, why is it that oil and water don't mix? Wait, why is that? Well, understanding overall polarity, thank you, exactly in the chat. Understanding the overall polarity of the molecule, then you realize, oh, wait, one molecule is polar, the other one is non-polar, okay? And then because they, at the overall polarity, they don't share that definition, then that's why they don't mix. Because when it comes to, you know, things mixing together, as we're going to explore specifically in chapter 9, because that's where we're going to dive in and understand how homogeneous mixtures come into one another, then you realize that, oh, it has everything to do with polarity. Because the things that share the definition of polarity, meaning if I have two substances that are polar, then they mix. If I have two substances that are non-polar, they mix. But if one is polar and the other one is not polar, that's why they don't mix. This is why it is important to understand overall polarity in terms of a molecule. So understand that the definition, so understanding overall polarity can be a complex concept if you go through the route or explaining it through vector rules. And indeed, when you take upper chemistry courses in graduate school, like I did, you may have to be exposed to vector addition and how vector addition actually explains. That's like the math behind all of this concept. I'm not going to teach you vector addition. I'm going to set to you guys a set of rules that, yes, it is based on vector addition, but it's going to simplify the concept of polarity, okay? And this is how we're going to handle it, okay? So I want you guys, when you have a molecule, that you're going to focus specifically on the electron group geometry of your molecule, okay? And then I'm going to give you a set of rules for when your electron group geometry is linear. I'm going to give you a set of rules for when your electron group geometry is trigonal planar, and a set of rules for when your electron group geometry is tetrahedral. Again, we are going to simplify the whole concept. Now, in the image that I found online, they like to use the word polar to define the bonds that we need, but it doesn't necessarily apply only to polar bonds. So I'm going to just erase the word polar, because it is true that this applies to polar bonds, but it honestly, it applies to any type of bond. So I'm going to erase the word polar, okay? So the rules that you guys have in front of you is for a linear molecule to be non-polar, you need two identical bonds pointing in different directions, okay? This is the idea of why when I was having a linear molecule, you guys, I was writing it left to right. So if you want to be creative and artistic and all that kind of stuff, that's okay. Do it on your own time. But when it comes to molecules, let's just train ourselves that if you have a linear molecule, draw it left to right, draw it horizontally, because it's going to help you to understand better this whole concept of overall polarity. Again, if you have a linear molecule and when you look at the left and the right, if they look the same, then your molecule is nonpolar. If it's not the same, okay, let me just write this in the notes. If the two bonds in a linear molecule are not identical, then the molecule is polar. Another thing that I want to specify with when it comes to identical in terms of chemistry. Identical means attached to an atom. Okay, that's all it means. Identical, attached to an atom. So I don't care if my molecule is attached through a single bond. Are you attached to oxygen? If your molecule has a double bond to oxygen, you're still attached to oxygen. So you can be holding oxygen with one hand, AKA a single bond, or you can be holding oxygen with two hands, which means a double bond. If you have a triple bond, that would be the two arms and a leg. But are you attached to the atom, okay, in question? So that's the case for linear. What is the case for trigonal planar? In order for something to be trigonal planar and nonpolar, you need three identical bonds. Okay? Similar to what I did or wrote for the first one. If the three bonds are not identical, then the molecule is polar. Let's look at the tetrahedral. For tetrahedral, remember, tetrahedrals have 4 electron groups. Those 4 electron groups need to be identical. If they are, then the molecule is nonpolar. If the 4 bonds or electron groups, right? Because at the end of the day, it's electron groups in a way, are not identical, then the molecule is polar. Okay. So let's go back and look at the molecules that we have here. And now we are going to define their overall polarity. So if you guys don't mind, I'm just going to make adjustments to these notes. Again, this is just what you guys see here that I'm making modifications on. This is just a copy of where I just took notes. Understand that all of this is going to be in the in-class notes. Don't be concerned that all of a sudden things are disappearing. All of this is going to be in your notes. So when you check later today on this, you will see that all of that is in there. Let me just crop this image to bring it here. Let me see if it fits. Okay, I'm able to cover that. Excellent. So let's look at the first example, H2S. Okay. So if I put here A, B, and C, which letter am I going to look at to determine its overall polarity? The rules for A, the rules for B, or the rules for C? I only see 2 answers. There's 28 of you guys. Excellent. I'm going to look at C. For those students that are like, wait, what? Why are we looking at C? Because my electron group geometry is tetrahedral. Okay? So the rule says that in order for my tetrahedral molecule to be overall nonpolar, it needs to have 4 identical bonds. If it doesn't have 4 identical bonds, then the molecule is polar. So what is the molecular polarity for H2S? Polar or nonpolar? P or NP? I got 1 answer, 2 answers, 3 answers. Excellent. I like to see those P's here. This molecule is polar because we don't have 4 identical things. We have 2 that are the same. We have 2 lone pairs and 2 single bonds, but no, in order for something to be non-polar, it needs to have 4 of the same. Great job. Letter B. What letter, in terms of the rules, corresponds to the rules that we need to apply to BEBR2? A, B, or C? Great. Letter A, because that's the rules for linear. My electron group geometry is linear. Again, if I look through the rules for letter A, what is my molecular polarity for BEBR2? Polar or non-polar? Excellent job, exactly. Non-polar. Okay, remember, bond polarity and overall polarity are not the same thing. Earlier in class, we learned that, wait, but B, E, and BR is a polar bond. That's okay, but remember, overall polarity is based on vector rules. So if a molecule has polar bonds, that doesn't mean that it is a polar molecule, because in vector rules, those 2 polar molecules those 2 polar bonds are going to be pointing away from each other. And according to vector rules, they cancel each other. So that's why the molecule is non-polar. So please do not confuse bond polarity and overall polarity. Different concepts, okay? Let's move on to SO3. Again, what's the letter that I'm going to look for in terms of the rules? A, B, or C? Great job, because my electron group geometry is trigonal planar. I'm going to look at the rules for B. So what is the molecular polarity for SO3? Polar or non-polar? I don't like to see those P's there because those P's are incorrect. I see some NPs, yes. This molecule is non-polar. And this is when students are like, Dr. Luz, why? What? No, 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 you said identical. And I defined identical to you guys a few moments ago. Let me just turn on my camera. And let me ask you guys a question. So, this is my Apple Pencil. This is what I'm writing notes with. Think about it in terms of SO3. My hand represents the bond to oxygen, right? My Apple Pencil is going to be my bond to oxygen. I have one hand. Let me ask you a question. Am I attached to oxygen? AKA, do I have an Apple Pencil in my hand? Yes or no? Let me change the scenario. Two hands on the Apple Pencil. Same question. AKA, this will be the example if having a double bond on oxygen. Thank you. So, am I holding an Apple Pencil? Yes. Am I holding an Apple Pencil? Yes. Let's rationalize it with the oxygen. Am I holding an oxygen in every direction? Exactly. Since I'm holding an oxygen in every direction, that means that I have 3 identical holds on an atom. I'm not on camera anymore. So if we look at the sulfur, the reason why that molecule is non-polar is because my sulfur is holding oxygen. In the case of the ones that are left and right, it's with one hand. The ones that is pointing down is with 2 hands because it's the double bond, but I'm still holding an oxygen. So that's why that molecule is non-polar. There's a question in the chat. Let me explain. H2S. So if we look at H2S, that's tetrahedral, right? So think about it. You're at sulfur, right? In order for something that is tetrahedral to be non-polar, it needs 4 identical things, right? 4 of the same. Look at sulfur. It's holding a hydrogen to one side, a hydrogen to one side, but then on top and bottom is holding lone pairs. The question is it holding the same item? No. If sulfur was holding 4 hydrogens, then it will be identical. So in the case of H2S, that sulfur is not attached to the same atoms in all 4 directions. It only has the same attachment in 2 things. And the rule is you need 4 identical bonds, 4 identical attachment to atoms. So in H2S, you only have 2. So that just cancels the rule and the molecule is polar. Did that help for H2S? Look at the beryllium. Beryllium, think about it. You're at beryllium, you're holding things next door. Are you holding bromines on either side and you're linear? The answer is yes. If you're linear, if you want to be nonpolar, you need to hold things that are the same on either side. Let's look at the last one, you guys. Okay? So based on the rules that we have gone over, what letter for the rules for molecular polarity do I have to look at? A, B, or C? Excellent. Letter A. Why letter A? Because my electron group geometry is linear. Now, remember, if I'm linear, I need identical. You know, I need to be holding the same atom on either side. So is carbon holding the same atom on either side? Great job. It's not holding the same atom. So if you're not holding the same atom, then that makes you exactly polar. Questions, understanding overall polarity or molecular polarity for an atom. Go ahead, Victoria.
Thank you. When will you post this lecture? Because there's parts that I need to listen to again.
Like in terms of the videos for today?
Yeah,
After office hours.
great, thanks. Thank you.
No problem. Any questions on overall polarity? Again, next week, you guys have lab 1, 2, 3, 4, 5 and 6. So lab 5 is the one for Lewis structures. I will encourage you, in order to prepare for the exam, which will be next week, next weekend, try to do lab 5 before it's due, even if you don't submit the answers, but it's going to be good practice because it's all about, I give you the molecular polyatomic ion, and then you have to, you know, fill this information. The tables for the lab look like this one. That's why I introduced it in lecture. Okay. Let me. Out of these, we haven't done the last 2, but it is in the in-class worksheet. Okay. Let's determine overall polarity for these 2. Okay, take a minute, look at the structures, and let's determine overall polarity for these 2. For carbonate, what is going to be the overall polarity? Francisco is the only one that got it. This is nonpolar. Alexa got it. Great. Elle got it. Dania got it. Think about it. Carbon is sitting in the middle. The rules that I need, because I have a trigonal planar, is that I need 3 identical attachment to atoms, meaning that I need to be holding an atom. I don't care if it's with 1 hand or 2 hands. Am I holding the same thing? Is carbon holding the same atom in every direction? Excellent. The answer is yes. So that means that I have 3 identical bonds around the carbon atom. Because this molecule is trigonal planar, then that means that since it has 3 groups that are identical, again, in terms of, am I holding the same atom? Then that's why it's nonpolar. Let's look at F, 4 electron groups, something that is tetrahedral. For chlorite, is that molecule polar or non-polar? Great job. This is polar because for tetrahedral, I need 4 identical groups. And I don't have 4 identical groups around chlorine. I only have two things that I'm attached to, which is the oxygens. I need four that are the same. So because this tetrahedral geometry that I have around the central atom does not have four identical groups, then the molecule is polar. Okay? Any questions about overall polarity?
So Professor, when we're looking at those, we're looking at like the actual element and it's attached to, not the bonding, right?
In terms of like,
The molecular polarity.
so when it comes to molecular polarity, I like to use the analogy of like, you know that when you guys go, it doesn't matter if you go to the safari park at the zoo, or even if you go to the mall, right? Like if you go look at a map, most of the time when you go to places, they say, you are here. So it indicates where, based on the map that you're looking at, it says you are here. So think about that when we're trying to do molecular polarity, the you are here is the central atom. So you're standing in the central atom. And then I'm looking around my central atom. And then I'm seeing, okay, down this hallway, am I seeing the same thing in all four directions in terms of a tetrahedral? Am I looking at the same thing in all three directions if I have a trigonal planar? Or if I have a linear, am I looking at the same thing in both directions that are opposite from each other? Okay, and if the answer is yes to that, if everything is the same in terms of what I'm attached to, okay, so if you're at the mall, you know how sometimes in the mall there's like multiple of the pretzel stores or multiple Starbucks, right? So if in either direction there's Starbucks and the mall is just linear, then that cancels each other. That is nonpolar. Yes, that's a good definition. So in the chat, there is, it says, a good definition for quote unquote identical could mean that the central atom is attached to a single type of atom via any bond. I actually like that. I'm going to copy that here. That may clear here. Thank you for that, Francisco. I appreciate it. This is going to be central atom is attached to a single type of atom via any bond. Love that definition. Thank you so much. So taking that into consideration, that's what, if the answer is yes, depending on your electron group geometry, then the molecule is nonpolar. If the answer is no, then the molecule is polar. That's how we determine overall polarity. So as always, I'm standing in the central atom and I'm looking in all of the directions depending on my electron group geometry. Any other questions when it comes to molecular polarity? Excellent. Since there are no questions, that's all for today.